Hello, in this clip I show you how to use Modelica in OMedit to simulate Peltier modules. But Modelica isn't just for electrical and thermal systems. It also works for mechanical and fluid simulation. Watch this to get all the necessary elements to get started with Modelica, and check out the full video for a real use case. Let's jump into OMedit, an open source Modelica editor from the Open Modelica Association. This software enables you to easily create, simulate and analyze multi-physics models. It includes the standard Modelica library, which contains basic blocks for simulation and many examples that you can easily run. To name a few, there are mechanics, fluids, electrical, which all have components, sensors and interfaces. And of course, you can create your own library or import other third-party libraries. However, Peltier module is not in the standard library. So, in this short tutorial, we are going to see how we can start creating a block for it to be used in the model of our setup. But first, we need to discuss the physics of Peltier modules. The simplified equations for a Peltier module are the following. They give the heat fluxes on the hot side and on the cold side and the voltage across the module. Heat fluxes are expressed in watts, which is a quantity of energy per second. If we detail each contribution, we first see the thermoelectric effect, which is proportional to the current. Then the module has an intrinsic resistance resulting in joule heating given by R times I squared. We can consider that this heat spreads evenly to both sides, increasing the heat on the hot side and decreasing the heat that can be transferred from the cold side. Finally, there is heat conduction due to the temperature difference, which is proportional to the thermal conductance K of the materials. In reality, all these parameters are temperature dependent. But to start the modeling, we'll use a simplified equation and use the equivalent parameters calculated from the values given in the datasheet from ATS and see what it gives. We'll later update the model if needed. So back to OMedit. You see the libraries panel on the left. As seen earlier, you find there the standard Modelica library. And below there is my custom library, inside which I created packages like thermoelectric or parts. For example, there are models for Peltier, chocolate, tank interface and so on. I'll detail the rest of the user interface as we go. So first, you may want to create a new package to organize your models. We'll call it Modelica Y for Modelica YouTube. I prefer to have models in different files, so I uncheck the option. We see 4 icons on the top left corner of the interface. It is here that you switch views to edit your models. As we are in the icon view, we can make an icon for it, and we see that it updates in the tree view. Note that if you close OMedit and reopen the application, the library won't appear in the tree view. For that, you need to load it automatically in the app preferences under Tools, Options, Libraries. Then we can start adding models to our library. We add a new model for a Peltier element. We'll start this time in the diagram view. We want to define the ports for the Peltier element. In Modelica, you have specific colors for the different types of pin. It can be found in the documentation. For example, blue is for electrical, red is for heat transfer, and real variables are blue triangles. You can also define custom connector types according to your needs. For our model, we need 2 thermal ports corresponding to the 2 sides of the Peltier and 2 electrical ports. We fetch those ports definition in the Modelica library. First, with the submenus Electrical Analog Interfaces, we drag and drop 1 positive pin and 1 negative pin. I go next in the Thermal Heat Transfer Interfaces submenu and I drag and drop 2 heat ports. If we check the text view, we see that the pins are added to reflect the diagram view. We can change port names for clarity, either in the diagram view or in the text view. We can go in the icon view and draw some shapes to reflect the device we are modeling. We make a rectangle, set in its properties the fill pattern to solid and choose a fill color. As we add more shapes, we see the icon update in the tree view. We are now ready to implement the model based on the equations we saw earlier. We could use the diagram view using drag and drop mathematical blocks, But for this model, I'm not going to do that. Instead, we can go directly into the text view and implement the model in text. Just before, we can create the model that will be used to simulate the Peltier block, so that we can see how it updates as we add elements to the text view of the Peltier model. We create a new model and call it Peltier simulation. We go in the diagram view and drag and drop the Peltier block. If we double-click the Peltier module, we see that there is no configuration available. So now, we go back in the text view. We import the international units system and we add a parameter of type SC.resistance. We save, we go back in the simulation model, double-click on the Peltier and see that there is now a resistance parameter that we can modify. But we will later set a default value for it. Next, we implement two other parameters that will be accessible in the configuration GUI and a few internal variables used by the solver. Those do not have the preceding parameter keyword. Then, in the equation section of the model, we implement the electrical and thermal equations. We define the voltage using the equation we saw earlier, and we need to ensure that the currents are fully defined. To do this, we add another equation for the current continuity, meaning the current entering the module equals the current exiting it. Without this, we will get an error. Next, we write the equation for QC and QH, and then connect them to the QFlow variable for each port. We can add comments and default values to the Peltier model. Next, we can finish to implement the simulation model. We add a ground from electrical analog basics. Then we need a voltage source. We can use a step voltage block found in electrical analog sources. We can also add the tank interface and the heatsink using the standard Modelica library. Both are heat capacitors that can be found in thermal heat transfer components. Heat capacitors have one parameter, the heat capacity, which is the mass times the mass heat capacity. Using standard blocks is quick, but once your model is set, you may want to update the icons to make it visually more representative. This makes it easier to identify parts and share your design with others. To give you an idea, here is what the simulation model of the setup can look like once details are added and icons are customized. Now we can set the model and the simulation parameters. The mass heat capacity of steel is 0.5 joule per gram per Kelvin, and the mass is 25 gram. So we write 12.5 joule per Kelvin for the tank interface heat capacity. For aluminium, it is 0.9 and the mass is 41 gram, so we write 37. We can set a step voltage of 2 volts after a delay of 5 seconds. It is a slow process, so we can make time steps of 1 second and set a duration of 300 seconds. We can run the simulation and check if the result seems correct. In the right tree view, we can see all the variables in the model. We can select the temperatures for the tank and the heatsink. As we expect, with a positive voltage, what we define as the bottom face is heating and the top face is cooling. Below, on the bottom right, there are tabs to switch between plotting and modeling. We can go on and add other blocks like convection, fixed temperature sources, thermal resistance, and a temperature sensor. The temperature sensor is not necessary at this time because internal variables can be monitored without a sensor. But we will need it when we implement a PID controller. The purpose here is to show you the conversion which occurs with a sensor, from a thermal port red square to a blue triangle, which is a real variable that will be needed for the PID. Later, we can close the loop by adding a PI control block and a constant variable for the target temperature.